So we've talked so far in this section about how we do limits of two variable functions, but is it possible to do limits of functions that contain even more than two variables? What if I had a function that was like f of x comma y comma z comma w, right? Like a four function or four variable function. Could I actually deal with a limit of this? And yes, you actually can. In fact, you can extend the definition that we had at the start of this section to account for functions with more than two variables. And it would look much like what I have here in the box. The only thing to note here is that we're introducing some vectors to kind of talk about inputs and different outputs here. So you'll notice that when I say f of x, and that's a bold-faced x, I really have some unknown number of inputs there at the moment. And in the same way, when I talk about x is approaching a, that's not x approaching a single number, that's x approaching a point with some unspecified number of components to it. Okay, so we can kind of think about those as vectors in larger spaces, and that's what we tend to do as we think about those pieces as vectors. Now, we're never going to actually deal with this specific definition here, but we are going to think a little bit about how I could deal with functions of three variables and doing limits for them. So interestingly, what I have to consider is the same sort of behavior that I had to consider when I was dealing with two variables. You might recall that when we were dealing with two variables, we had to oftentimes think about a point that we wanted to approach. Maybe we were approaching a point like 1, 0, and we had to think about paths that could lead me to 1, 0. We often thought about a lot of different possible paths that could take me through that point. And the reason that we thought about the xy plane as we did this is because the xy plane represented the input variables of a function f of xy, right? So we were looking at the domain and picturing the domain. Well, if I had a function then that was like f of x, y, z, and it had three input variables, then to kind of imagine its domain, so to speak, I'd actually have to imagine the entirety of the x, y, z coordinate system. And so in this case, if I wanted to say have a limit that was approaching, say, a point like 0, 0, 0, I would have to come up with a curve or a path in 3 space that would take me to the point 0, 0, 0. So notice how this works with something like example number 8. Okay, here I have a function. You can imagine this as my f of x, y, z. It's yz over all this stuff down here. And I want to do a limit of this as x, y, z approaches 0, 0, 0. Okay, now the first thing to note is that all of this stuff here is again equal to fxyz, which for the moment, for the sake of argument, let's just call k. So this is technically like a formula with 4 variables in it. Now, unfortunately, that means that I really can't picture what this looks like. I can't draw you the 4 variable thing. That would mean I'd have to go beyond the world of 3D. This is a 4D thing. So I can't really picture what this is, but I can still picture its domain. And since I want to go towards 0, 0, 0, I'm going to have to create curves existing out in 3 space that are going to travel through the point 0, 0, 0. So up here, while I was able to do simple like algebra, calc 1 style functions, in here, since I'm moving through 3 space, I'm going to need functions that exist in 3 space. And in order to do that, I'm going to have to come up with functions like vector functions. So notice here, like I have highlighted in green, this is a perfectly reasonable vector function that actually I could graph and takes me to the point 0, 0, 0. Notice this vector function says that all the points on this function have an x-coordinate of 0, a y-coordinate of 0, but their z-coordinate varies. So if I was to try to draw what this function looks like in 3 space, it looks like this. Here's my r of t. It just so happens to be the z-axis. This is a formula that takes me right up and down the z-axis. And so, of course, that's definitely a possible path that leads me to 0, 0, 0. So let's go ahead and see what happens to this limit along that path. Okay, so I'll say if we approach 0, 0, 0 along r of t equals 0, 0, t, then let's see what happens to our limit. Our limit now of x, y, z, notice can be replaced with what my function is defining those components as. Notice x is always 0, y is always 0, and I end up with t in place of z. And I need all this to just approach 0, 0, 0. How is this going to ultimately affect what I'm doing the limit of? Well, notice here that I'm going to get 0 times t in the numerator, and then I'm going to get 0 squared plus 4 times 0 squared plus 9 times t squared. But ultimately, this is just a limit with a single variable t of 0 over 9t squared. Okay, so this is 0. But notice that this should be very similar in the generic sort of style of approach that we're taking to what we did before. The tough part is coming up with the new paths, because we have to come up with vector functions to do it. Okay, can we come up with another path that might work here? I think we can. There's actually tons of paths that we could come up with. And we don't even necessarily have to be able to picture what all of these paths look like. So what if I said something like, if we approach 0, 0, 0 along, let's come up with a new function here. I'll call this r number 2 of t. But I'm going to create this as 0tt. Okay, that's going to be my formula that I'm going to end up with, or the formula. And I think that's a path that leads me to 0, 0, 0. Now, part of the reason that I know that is because, notice, can you find a value of t that you could plug in so this vector function spits out the vector 0, 0, 0? And like, yeah, super obviously, if I plugged in 0 for t, then this vector function would be pointing me directly to the point 0, 0, 0. So I have this red function here compared to the green one, and I'm not quite sure exactly what this red function looks like. I don't think it's the x-axis or the y-axis or the z-axis. It's something else. You could go ahead and attempt to graph it. I'm guessing it's going to be a line, because it looks like I'm going to have a line here. And it's a line that has some sort of a slope, if you will, in the y and the z direction. So maybe it's going to be something that's kind of like this, if you will, going through 0, 0, 0. And again, I don't necessarily have to picture it to be able to use it, because what I'll notice here is that if I go ahead and try to calculate this limit, notice now that my y and my z have been replaced with t. So that's going to give me t times t in the numerator, and that's going to give me 4t squared plus 9t squared in the denominator. So again, this is still going to be a limit where I just have t approaching 0, but it's going to be of t squared over, it looks like 13t squareds. Limit to that, 1/13. So I can easily see here, since 0 doesn't equal 13, this limit does not exist. Okay, so the process is exactly the same. We would have to, if we wanted to show that this limit did exist, we would have to show that it exists again along every single possible path we could ever create, now in 3 space, that goes through 0, 0, 0. So hopefully you feel fairly comfortable with kind of what's happening here. The toughest part is coming up with those red and those green functions that we're kind of using. But sometimes if you just focus on, is there a value of t I could plug in that could make this turn into the point I want to approach, that's an easy way to kind of generate lots of functions rather quickly.